Discussion. An axiom of animal behavior is that the movements of an organism at any time will, in part, be caused by the physical conditions of and variations in the organism's environment. Its genetic framework and past experience up to that moment will determine how the organism will react in response to a given change in any one or more of these conditions. In my study of these crabs, I ignored or only briefly considered many of the abiotic factors. Also, I left uninvestigated the genetic framework of the animals and the changes in behavior both during maturation and over long periods of their lives. Rather, by observation and experimentation, an attempt was made to investigate those behavior patterns, which are elicited and controlled for the most part by the presence and movements of individuals of the same species. Distribution and dispersion. The first aspect of social behavior encountered in this approach was the statual distribution of the crabs in nature. The species of hermit crabs examined are confined to warm marine waters from the shoreline down to a depth of about 30 meters. Within these broad ecological limits, genera and species are more narrowly confined by various physical aspects of the environment. Paguridae species are able to live in deeper waters, and around Curacao, Paguridae catenati is limited to deep water areas. Calcinus tibicen is more tolerant for some variation in depth, but is not found in waters as deep as Paguridae catenati. The genera Pagurus and Pilopagurus are limited to slightly more shallow areas than Calcinus, and Clibinarius tend to be even more shallowly distributed. From another viewpoint, Clibinarius and Pagurus bonarensis are able to inhabit shallow, turbid waters, such as in the inner bays of Curacao. These areas are very rich in organic deposits, both on the mudflats per se and in the slightly deeper bay bottoms. This is especially true in comparison with the organically poor marine waters of the Netherlands Antilles. Clibinarius cubensis and Clibinarius vitatus in Florida are able to inhabit mudflat areas more readily than Clibinarius tricolor. Clibinarius antillensis is found in the same mudflat environment, but is much smaller and probably feeds on smaller particles. Pagurus bonarensis is able to invade even more turbid waters and exploit this detritus-rich niche. Another important environmental factor is the presence of food. Hermit crabs in general are omnivorous. All the species studied were readily maintained in the laboratory on a diet of canned dog food. Individuals of all species would attack the macroscopic pieces and tear them apart with one or both chelipeds, and further macerate the particles with their maxillipeds and other mouth parts. Large pieces of both brown and green algae were less actively manipulated. Although most species did appear to feed upon macroscopic algae to a limited extent, the level of feeding activity of a group was more readily increased by the introduction of either animal matter or small detritus-covered rocks. In the field, all species appeared to concentrate their feeding activity largely on detritus matter. Experiments described in an earlier section of this paper showed that individuals of Clibinarius tricolor orient chemically toward a detritus-covered rock during the species' period of feeding. Macroscopic particles of animal matter were fed upon by hermit crabs as well as other crustaceans. However, in all species the majority of the individuals appear to be feeding on detritus material during the majority of the species' feeding period. In areas where the bottom is either sandy or composed of clean rocks, few or no individuals of any species of hermit crab were found. The density of hermit crabs, all species considered, varied from 0 to 928 individuals per square meter in the areas sampled. The average density of the selected areas measured was 220.5 hermit crabs per square meter. In addition to the above-mentioned factors, the distribution of individuals of a species within any given area may be influenced by the distribution of rocks, corals, and other large objects. Positive phygmotaxis and/or negative phototaxis, see Dreswina 1907, would provide a behaviorally simple way of congregating individuals under large rocks. Such a type of distribution was observed in Calcinus tibicen. Distributions formed in a uniform laboratory environment were random. The distribution of Pagurus marshi within favorable areas was almost random in the field. Even after considering the limitations set by the variations of ecological and microgeographical conditions, the distribution of individuals of most of the shallow water hermit crabs studied was not random. Non-random distributions are the rule among animals, Wynne Edwards 1962, and have been mentioned in a qualitative way for some European species of hermit crabs, Bond 1902. The degree of contagiousness both in the laboratory and in nature varied from species to species and within species depending upon ecological conditions. Clibonarius tricolor was the most consistently highly gregarious species, although Pagurus miyamensis and Pagurus bonarensis were also consistently distributed contagiously. Even individuals of those species which were too uncommon or were distributed in places that made measurement difficult, i.e. Pylopagurus operculatus and Pagurus pygmaeus under rock piles, appeared to be distributed contagiously. In Clibonarius tricolor, Pagurus miyamensis, and Calcinus tibicen, groups are formed which appear to be relatively stable from day to day. In Clibonarius tricolor, the individuals form and/or maintain the group guided by chemical orientation to conspecific individuals. Pagurus miyamensis and Calcinus tibicen appear to orient toward factors of the local physical environment when forming their groups. In the shallow waters near a marine shore, it may be advantageous not to depend on the permanence of particular rocks for maintaining group stability. The establishment of a definitive and stable aggregation may be more essential in Clibonarius tricolor due to its limitation to shallow water. Groups exposed at low tide retained a small but consistent amount of moisture around the inner members, while isolated individuals usually moved to deeper water during low tide. By aggregating toward one another, groups of Clibonarius tricolor eliminate dependence on rocks or other larger objects in the environment, which could be displaced. The diurnal aggregations of any species may be of an advantage insofar as predators can more rapidly learn that hermit crabs are protected by their gastropod shells. Another distributional factor was noted for Clibonarius tricolor. Within the large aggregations which this species forms, the large males tended to be on the periphery of the group. Experiments described in an earlier section showed that several stimuli contribute to the formation and/or maintenance of these aggregations. In the case of Pagurus miyamensis, the combination of a detritus-covered rock with conspecific individuals upon it acts as a source of chemical substances to which the crabs orient. Individuals of Clibonarius tricolor will orient to a chemical coming from a group of tricolor, or Calcinus tibicen. This grouping pheromone is not species-specific, but tests with fiddler, uca, and spider crabs, mithrax, indicated that this chemical is not a property of all crustacea. It would be hard to imagine how a chemical orienting stimulus could work over any distance in the turbulence of a marine shore. Because of the complexity of the movements of the transporting medium, it is assumed that in nature these chemical stimuli are effective in directing orientation only over relatively short distances. As shown by the work of Bossert and Wilson, 1963, even traces of pheromones in microgram quantities can effectively excite through thousands of cubic meters of space, but their directive potential is greatly reduced by the turbulence of a medium such as the waters of an ocean shore. Laboratory tests indicated that the gastropod shell does not act as a source of a distance orientation chemical, but that there may be an ethanol-soluble chemotactic factor present on the shells. Clibonarius tricolor did orient preferentially to a pile of empty shells when they had been washed in seawater. However, after the shells had been leached in ethanol, no preference was shown between a pile of shells and a pile of small stones. Even so, the crabs did orient toward both the shells and stones in preference to the control areas, indicating the possible presence of a tactile element in the aggregation formation of Clibonarius tricolor. Tests concerned with any visual cue in aggregation formation were negative. Diel cycles. The diel cycle variation in the locomotor and feeding activity of these crabs appeared to conform to one or the other of two general patterns. The more common was a diel cycle in the strict sense, i.e. varying in the same way each day and controlled or guided by the physical changes associated with the 24-hour cycle. This was found in Paguristes grayi, Paguristes cadenati, Pagurus marshi, Pagurus miamensis, Pagurus pygmaeus, Calcinus tibicen, Pilopagurus operculatus, and Clibonarius tricolor. It is, of course, possible that the cycles of these species are affected by factors whose variations are of a different period. However, the principal variations are correlated with variations of a daily nature. The second pattern was the tidal variation that was possible. The second pattern was the tidal variation that was possibly present in Clibonarius cubensis, Clibonarius vittatus, and Pagurus bonarensis. An activity pattern based on tidal movements would be logical for these species, and field observations indicated that this may be the case. If the crabs are to exploit the rich environment of the mudflats and yet avoid being exposed completely to air during low tide, their activity must be correlated with the rhythm of tidal variation. Among those species with a diel cycle, several types of patterns appeared. The most common was a nocturnal, crepuscular peaked pattern. Clibonarius tricolor, Clibonarius antilensis, Calcinus tibicen, Pagurus miamensis, Pagurus pygmaeus, and Pilopagurus operculatus move about and feed during the evening and at night, and show peaks in their locomotor activity at dawn and dusk as they return to and move out from areas of diurnal aggregation. In all these species, the diurnal group, whether formed through true gregariousness or orientation to local environmental features, is a quiescent aggregation. The organisms move about little and feeding movements occur at a low rate during the day. In late afternoon or evening, the group breaks up and the crabs move away several meters, feeding throughout the night. Shortly before sunrise, the individuals move back into the areas of diurnal grouping. The cycle of Pagurus marshi differs from the above in that its locomotor activity level is highest around dawn. The level of activity is at a moderate, approximately equal level during the day and night, but decreases markedly at dusk. In both species of Paguristes studied, the pattern is even more anti-crepuscular with low levels of activity at dawn and dusk. It is reasonable to assume that both predators and competition may have been important in the evolution of the cycles of the three species. Pagurus marshi differs from other shallow-water hermits of Curacao in the boldness of its diurnal movements. It moves about on top of rocks and coral rubble much more consistently than other species. The detritus camouflage and the decrease in activity at dusk may allow it to survive while thus exposed. Aggressive behavior. The specific activities of hermit crabs at any moment are strongly influenced by conspecific individuals. The various actions and reactions of crabs which come into contact with one another have been described about in general and specific cases. The model presentation experiments described above showed that these movements and positions are visual stimuli. The chemical orientation tests and the tactile stimuli tests carried out with pagurid species showed that stimuli affecting other sensory modalities may affect the specific movements that an individual executes at any given instance. A striking fact discovered in this study is the similarity of the behavior patterns among the species observed. See Table 11 for a qualitative summary of the behavior patterns observed in all species. The closest similarity was observed in the general aggressive interactions. Certain types of movements were observable in all species studied. These classes of movements were also seen in several other species of hermit crabs, though these species were not observed enough to merit a detailed treatment. These included Dardanus venosus, H. Milne Edwards, and Petrocurus Diogenes Linnaeus in Curacao, and Pagurus longicarpus, Say, in Massachusetts. Variations of the more common aggressive displays occurred in some species. The forward ambulatory movement of Clibinarius cubensis and the side-arm cheliped extension of Pilopagurus operculatus are examples. However, these variations were always less frequent in the aggressive interactions of the species. This rareness makes the establishment of the display function of these behavior patterns more difficult. If we were to use the simple information measure provided by the formula H equals dash sigma pi log pi, where pi is the probability of occurrence of even p, Shannon and Weaver, 1949, rare events do not greatly increase the amount of information in a system. These rare events, even if very effective in eliciting a change in the behavior of the animal, would not increase the amount of information in the system very much. However, if effective biologically, these rare events may be very important, thus raising an important qualification in the biological use of this information measure. The common aggressive displays, the cheliped extension and the ambulatory raise, occur rather frequently in all species, with the possible exception of Petrocurus Diogenes. The frequency of occurrence varies from species to species, but these display are not rare in any. The fact that similar movements occur in all members of a group may have several bases. It is unlikely that these movements have been inherited by all living species from a common ancestor. Perhaps any organism with the morphology of a hermit crab, therefore classified as such, would execute such movements in an aggressive situation. A third possibility is that the not uncommon event of interspecific meetings has necessitated the development of a common language. Crabs of different species, genera, and families do meet, and if they could not communicate on a signal level, such meetings could more frequently lead to physical aggression and damage. However, the size differences between species decrease the use of aggressive displays in interspecific encounters. A smaller crab will usually retreat or pull back into its shell at the approach of a larger crab, whether conspecific or not. Indeed, the aggressive displays, in particular the ambulatory raise and the cheliped presentation, make the displaying animal appear larger, and their effectiveness as aggressive signals may be related directly to this property. It may be recalled that in vertebrates, agonistic posturing commonly includes swelling, fluffing. It may be recalled that in vertebrates, agonistic posturing commonly includes swelling, fluffing of feathers, or raising of crests to increase apparent size. Whatever the basis or bases for the similarity of the aggressive displays among hermit crabs, the differences observed in the frequency of occurrence and manner of execution for the most part follow phylogenetic lines. Thus, the behavior of Clibinarius tricolor and Antillensis are almost identical, as are the patterns of Clibinarius cubensis and Vittatus. However, these two pairs are rather distinct from each other and behaviorally could be put in separate subgenera. The general speed of movement, manner of walking, rigidity of appendage during the execution of an ambulatory raise, and details of shell fighting all separate these pairs. Moreover, the preliminary observations of the sexual behavior of Clibinarius cubensis and Vittatus indicated even more definite separation and closer relationships with the genus Paguridae. Baughan, 1902, has suggested that the genus Clibinarius was derived from a Paguridae-like ancestor. The behavior of Calcinus tibicen is similar to that of Clibinarius tricolor and Antillensis. The similarities are more numerous than those between the two species pairs within the genus Clibinarius. However, the unequal and larger chelipeds of Calcinus tibicen are used more, and their movements are stronger aggressive stimuli than the chelipeds of any Clibinarius species. Provenzano, 1959, has mentioned that the differences in cheliped morphology is one of the few areas of difference between the genera. As described in the earlier sections of this paper, this similarity between Clibinarius tricolor and Antillensis and Calcinus tibicen extends also to the details of their sexual behavior patterns. The Pagurid species studied can be ranked according to the size of their major cheliped, frequency of use, and importance of the major cheliped extension display. With reference to the size of the major cheliped, the order is Pagurus bonarensis, Miamensis, Pygmaeus, Marschi, and Pilopagurus operculatus, going from the narrowest to the widest dactyl. Order by frequency of use. The species arrangement would be changed by placing Pagurus bonarensis between Pagurus marshy and Pylopagurus operculatus. Using the chi-square values of the results of the static model presentations as a measure of importance or effectiveness, the order is the same as the morphologically based one. Pagurus bonarensis, chi-squared equals 17.77. Pagurus miamensis, 21.19, Pagurus marshy, 21.3, and Pylopagurus operculatus, 24.2. Yet in all these crabs, one or more types of ambulatory movements also occur and are effective aggressive displays. The ambulatory rays of Pylopagurus operculatus occurred quite frequently, 293 times in 1,021 interactions, and did act as a stimulus in the model presentation tests. Chi-squared equals 11.27. The similarity of Pagurus miamensis and Pygmaeus is evident in their behavior patterns as well as in their morphology. However, they do not appear to be as similar as the species pairs mentioned in the genus Clibinarius. The genus Pylopagurus is very paguroid in its behavior. Indeed, among the species studied in Curacao, Pylopagurus operculatus would appear to be the most strongly different from the Diogenid crabs. Dislodging shaking is very strongly developed. The spasmodic shaking movements dominate shell fighting. Its general movements are very rapid, and the movements of the chelipeds are more frequent and effective in aggressive interactions. It is possible to speculate upon the development and ritualization, Tinbergen, 1951, of these aggressive displays. The walking movements of all hermit crabs involve some vertical elements. In Clibinarius tricolor and Calcinus tibicen, these elements are small, while in Clibinarius cubensis and Pagoristes cadenati, they are quite noticeable. Moreover, as one crab starts to climb over the shell of another, it raises its ambulatories even more markedly. The fact that the outward motion of the ambulatories makes the animal appear larger is probably important. Individuals which avoided physical damage by conspecific individuals by retreating from a larger individuals which avoided physical damage by conspecific individuals by retreating from a larger crab as it walked toward them would be more likely to survive and reproduce. Likewise, individuals would be selectively superior if the physical damage between crabs was further reduced by the exaggeration, when meeting a conspecific crab, of the vertical element of the ambulatory movements involved in walking or climbing. These improvements in communications would also increase fitness at a population as well as at an individual level. In a similar manner, the feeding movements of the chelipeds could have become exaggerated and ritualized as aggressive displays. It is to be expected that more aggressive interactions would occur at a food source than elsewhere. As these crabs feed, their chelipeds move back and forth between the substratum and their mouthparts. The motion need only be exaggerated in its forward component, and a cheliped extension would have been executed. It is plausible that the evolution of unequal chelipeds is, in part, a specialization such that crabs can simultaneously display aggressively and feed with their minor cheliped. Shell fighting. Unlike the general aggressive repertoire, shell fighting and sexual behavior patterns are strongly divided along familial lines. The general framework of shell fighting behavior is similar in all species, and those factors which were indicated as important for Clibinarius tricolor probably are effective in all species. That is, a smaller crab can very largely get a larger, non-soft crab out of its gastropod shell. that females may have a slight advantage in shell fights, and that recently molted individuals are more subject to attack and more likely to lose a shell fight. In addition, observations indicated that in all species, with the possible exception of Paguridae's species, the application of direct force between crabs does not take place, but rather the behavior patterns which an attacking crab goes through act as signal stimuli. Several personal communications and the papers of Bouvier, 1892, Bon, 1903, and Ali and Douglas, 1945, have indicated rather clearly the idea that the evacuation of one crab by another is a matter of force. However, almost without exception, these observations have been of fights between an artificially shell-less crab and one in a shell. Such a situation could exist in nature, but all the fights I have observed both in the laboratory and in the field have been between two shell-inhabiting individuals. These observations include two shell fights between individuals of Pagurus longicarpus, the species observed by Ali and Douglas, 1945. These fights followed the general Pagurid pattern and included both rapping and spasmodic shaking. The actual effective stimuli of a shell fight which affect the defending crab's peripheral sense organs and eventually its CNS can only be guessed at. However, behaviorally it is clear that the actions of the attacking crab which result in eviction of the loser are acting at a signal level. The rapping motions of Diogenid crabs and the rapping and spasmodic shaking in Pagurid crabs are probably negative situations, which the defending crab would avoid if possible. Evacuation is one means of avoiding them. The loser of a shell fight does not appear to be physically damaged in any way. The first actions of an attacking crab are to either attain an opposed position directly or to turn the other crab over and over while holding the shell in its ambulatories. Both Rees's 1962a, 1963, and Grant's 1963 work on the shell-selecting behavior of hermit crabs have indicated that the weight of a shell is an important factor in selection. It is probable that the attacker is visually, and in the case of a recently molted defender to be, chemically oriented to a shell of approximately the right size. Then, through its initial turning and cheliped insertions, the crab could measure the shell more closely. These measurements could include weighing the shell and occupant. The positioning behavior which precedes rapping or spasmodic shaking may also allow the crab to judge some variable of the shell, as well as orient itself for the behavior patterns to follow. Preliminary observations of the shell fighting of Dardanus venosus indicated that in this species, the rapping movements follow the pattern set by the positioning movements. That is, the positioning movements involve a side-to-side horizontal figure-8 motion by the attacking crab. In the same way, the rapping is not carried out directly up and down along the midline of the shell aperture, but raps are executed first on one side and then on the other. Often the attacker gave 2 raps on the left, raised itself and moved to the other side of the aperture and executed 2 raps. Sometimes when the crab's apertures were directly opposite, a slight downward motion occurred, but just a dip, not a full rap. The raps were generally Diogenid in nature of execution. The fact that the repertoire of Pagurid crabs is more complicated than that of Diogenid crabs can be interpreted in several ways. Spasmodic shaking may have been present in the ancestral behavior pattern and could have been lost in Diogenid crabs. Conversely, it may have been added onto the ancestral pattern in the Pagurids, while the Diogenid line evolved no such complications. It could be argued that making noise, rapping, in the deeper waters characteristic of the Paguridae, as a whole is undesirable, in that it could attract predators, while such noise would be undetectable among the surf and snapping shrimp sounds of the shallower areas which are characteristic of the Diogenidae as a whole. The argument would be weakened by the Diogenid pattern of Paguridae species, unless one considers the shortened series of raps and overall reduction in number of raps per fight, characteristic of Paguridae catenati and grayi. Associated with this reduction in these species is the apparent use of some force in pulling the loser out. It may be that this type of behavior is not as advanced, less signalized in this genus. After the shell-fighting behavior patterns are accepted as symbolic stimuli, a possible explanation of their ritualization may be given. If a crab did grasp the limb of another with its cheliped and attempt to pull it out forcefully, it might not be successful on the first pull. A series of tugs by an attacker could be given added force by bringing the large abdominal muscles into play and using a rapid downward motion of the attacker's shell to apply a sudden outward force on the limbs grasped by the attacker. However, this strategy could often lead to autonomy of a limb by the defending crab. This would not only damage the defending crab, but it would also not obtain the fought-for shell for the attacking crab. The evolution of a signal-level strategy, such as present in most species, would eliminate or greatly reduce physical damage between combatants, and at the same time assure the possibility of attainment of the shell by the attacking crab when it is larger. Sexual behavior. The difference between the families in the species' sexual behavior patterns are also marked and consistent. The differences have been discussed in the species descriptions, in particular under Clibinarius tricolor and Pagurus miamensis, and are summarized in Table 11. In the Paguridae, the similarity in the motions involved in shell fighting and sexual behavior is worthy of mention. Although affected by different movements, spasmodic shaking and precopulatory jerking both involve a short, rapid movement of the passive crab toward the active crab. As mentioned above, the sexual behavior of Clibinarius cubensis and vittatus more closely resembles that of Paguridae catenati, while Clibinarius tricolor and antillensis and Calcinus tibicen show many similarities. The closely related pairs of Clibinarius tricolor and antillensis and Pagurus miamensis and pygmaeus appear to illustrate a case of ecological versus sexual isolating mechanisms. That is, in Curacao, Clibinarius tricolor and antillensis are ecologically separated for the most part, and their mating patterns appear to be very similar, if not the same. Pagurus miamensis and pygmaeus live in the same microenvironment, and their patterns are very different. In fact, pygmaeus's pattern is the most divergent among the pagurid species observed. It would appear that the presence of two closely related species in the same microenvironment has necessitated the development of very different and distinctive patterns of sexual behavior. It is interesting to speculate on the possible basis for the difference in the psychological behavioral sequence in the mating behavior of Pagurus bonarensis. In the majority of matings in all other species observed, the female released mature larvae, molted and then copulated. The sequence in Pagurus bonarensis appears to be copulation, release, and then molting. The environment of bonarensis presents several features that might be disadvantageous for recently released larvae. The water temperature is slightly higher during the day. The oxygenation level is probably rather low, and wave action is so slight that the larvae might easily settle into the mud bottom and die if they do not swim away, not into the shore, on their own. Thus, perhaps it is necessary for the female to migrate to slightly deeper waters of Paguridae Bay to release the larvae. This would present no problem in the copulation-fertilization sequence unless the male does not migrate, and fertilization of the new eggs occurs in deeper waters after egg release and molt by the breaking open of the attached spermatophore filaments. In other bay-inhabiting species, such a movement to different ecological conditions would involve a much shorter movement just off of the mudflats, which have to be vacated at low tide in any event. The slope of the bottom in the area inhabited by Pagurus bonarensis is such that a longer migration would be necessary. Mating behavior in the populations around Miami, where this species is rather widespread, appears to follow the normal pattern of release, molt, and copulation. The more common sequence of mating activity for crustaceans is illustrated by Clibinarius tricolor. Shortly before she is ready to molt, a female is contacted by a male and he begins an extended series of precopulatory behavior patterns. After the female has molted, with the help of the male in some cases in Clibinarius tricolor, a series of behavioral acts leads to copulation. In Clibinarius tricolor, there follows a period of post-copulatory behavior, which appears to be similar in movements to the precopulatory activities. This activity may aid and or protect the female while she is getting the new eggs in place. Social dominance. The observations of laboratory groups over a period of days provided several interesting sets of data. Considering the aggressive behaviors of the whole group, it is clear that the aggressive activity of a group declines rapidly over several days and reaches a low, perhaps constant level. This was observed in all three species studied, Clibinarius tricolor, Calcinus tibicen, and Pagurus miamensis. The amount of aggressive behavior decreased rapidly after initial introduction, placement in a new tank, and a second isolation reintroduction. The lower level of aggressive behavior seen on the days following one of the three treatments is probably more representative of the conditions present in nature. The measurements of the diel activity of the various species indicated that the amount of aggressive activity varies throughout the 24 hours. This cycle is correlated rather well with the variation in general locomotor activity. Variations in aggressive behavior as measured under laboratory conditions appeared to be present in nature also, and are only to be expected if the animals maintain a relatively constant aggressive predisposition. The interactions of the individuals of a group of animals may occur according to two sets of rules. Operating under the first set, every interaction is decided by the interaction of two anonymous organisms. That is, the two organisms are of a certain size, physiological condition, and each have a history of social interactions which may affect their future actions in a general way. However, the effects of an animal's history are not oriented towards specific individuals, but rather produce behavioral predispositions. Seward's 1946 work on submissive behavior in the rat illustrates such predispositions induced by behavioral history. According to the second set of rules, the outcome of any given interaction is mainly determined by the history of interactions of the animals with respect to each other as specific individuals. The organisms recognize one another, and the outcome of the interaction is decided largely by the effects of previous encounters. This second set of rules operates in the maintenance of a dominance or peck order, while the first set plays a more important role in the establishment of the order. A group of organisms may interact in a stable, ordered fashion and be operating only according to the first set of rules. That is, every interaction is decided strictly on the basis of the interaction of independent operators. Consistent, ordered differences between individuals could, however, produce a consistent, ordered pattern of interactions. The groups of crabs set up in the laboratory did show a certain amount of order in their patterns of interactions. The combining of the interactions occurring when the group was first formed, with the results of later interactions, may have badly obscured the outcome. However, let us examine the manner in which such data can be treated. If the groups are arranged in a peck-right or absolute straight-line order, as was done in the top matrix of figures 32, 33, and 34, it is observed that the results of a number of interactions are not consistent with such an arrangement. Even when arranged in a peck dominance or percentage straight-line order, there are interactions which do not appear to fit such a pattern. Thus, although the interactions of most of the groups were far from randomly arranged, as shown by the DHS, they did not completely fit any of the standard types of dominance orders. The covering matrix for each group is also of interest. In any sort of social order, except an absolute straight-line order, such a matrix would be of the type observed in these crabs. That is, in many of the groups of crabs, almost every individual was chain dominant over almost every other individual. In an absolute dominance order, the animals would be chain dominant over 19, 18, 17, 16, etc. organisms from the alpha individual down. This was hardly the case in these groups. The results of the chain dominance matrices agrees closely in many ways with the subset groupings which were based only upon the first-order interactions. For the most part, subset grouping based on the covering matrices differ little from those presented. What this agreement points to is the probable total scope of the dominance hierarchy statistic. That is, although it is based on the first-order interactions, it probably reflects the order present in the group, even when considering all possible chains of interactions. However, what the DHS tells us is of limited value if we are interested in true dominance orders. It does definitely prove that the results of the interactions are not arranged at random, and that the crabs are definitely ordered in their interactions, even though this order is not perfect. The average DHSs for the groups of the three species are 3.459 for Paguridae miyamensis, 3.224 for Clibinarius tricolor, and 2.849 for Calcinus tibicen. All are highly significant, p less than or equal to 0.01. That is, if A is dominant over B and B is dominant over C, then there is a good probability that A is dominant over C. However, the mechanism of this dominance is not elucidated by the DHS. In order for this arrangement to be a true dominance order, the crabs must be recognizing each other as individuals, with a certain position relative to themselves. The problem of proving that the crabs are recognizing one another has not yet been solved. Certain readily observable variations in the data point toward such a system. If the system were based on independent events, which would probably be strongly size-dependent, there should be a correlation between the size range of a group and the perfection of its dominance order. That is, if size were very important, the perfection of a dominance order would depend in part upon the size distribution of the group. Rank order correlation coefficients between size range and the DHS for each group were insignificant, p greater than 0.1. C equals plus 0.3 for Paguridae miyamensis, C equals minus 0.4 for Clibinarius tricolor, and C equals plus 0.3 for Calcinus tibicen. In argument against within-group recognition are the variation patterns of the percentage of interactions with displays shown by each species, figure 29, 30, and 31. If individual recognition was playing a part in the interactions of the group, the percentage of interactions with displays should have decreased as group order was established. In all three species, this percentage inconsistently varied about an average approximately equal to the percentage on the first day. The problem of recognition was not considered in Pardy's 1948 work on dominance order in Polistes Gallicus. In the rather extensive work on social orders in Cambarellus, Lowe 1956 demonstrated several variations that point toward the presence of recognition and true dominance orders. These facts included subordinate animals retreating at less extreme forms of aggression over a period of time, and the fact that a crayfish maintained or lost little of its dominant position after loss of a cheliped. The detection and demonstration of a true dominance order in the interactions of a group is a difficult problem, and more than a matrix of interactions is required. The mathematical methods herein presented can establish that a group is ordered to a certain degree, but the basis of this ordering is not so easily measured. Through this work, a description of the behavior patterns in a series of hermit crabs has been presented. Based upon this descriptive experimental basis, a more complete study of the communication systems involved is being carried out. Hazlett and Bossert, 1965. Summary. 1. The social behavior patterns of 12 species of hermit crabs found in the waters around Curacao, Netherland Antilles are described. All species showed marked similarity in their aggressive displays, the most common of which are movements of the appendages, called here the ambulatory raise and cheliped extension. 2. Model presentation experiments proved that these positions are effective visual stimuli. These tests also showed that the white tips of the ambulatories of Clibinarius tricolor are aggressive stimuli. 3. Paguride crabs showed a dislodging, shaking behavior pattern when crawled upon by other individuals. Experiments were carried out to determine the relationship between stimulus weight and the size of a crab showing this pattern. 4. Measurement of laboratory and field distributions indicated that some species are truly gregarious. Clibinarius tricolor, Pagurus miamensis, Pagurus bonarensis, while other species are contagiously distributed due to orientation to certain physical factors in their environment. Calcinus tibicen. 5. Laboratory and field tests showed that individuals of Clibinarius tricolor form relatively stable groups. The groups are formed and/or maintained through orientations to a grouping pheromone. These groups are formed daily after the crabs have been dispersed over the nightly feeding area. At night, individuals of Clibinarius tricolor oriented chemically toward a detritus-covered rock, their normal food source. Groups of Pagurus miamensis also oriented chemically to a group of conspecific individuals established on a rock. Individuals of both species oriented toward a conspecific group only during the day. 6. Diel cycle measurements were carried out for most species. The most common pattern was a nocturnal, crepuscular peaked cycle, although Paguristes species showed an anti-crepuscular pattern. 7. Individuals of all species fought one another for gastropod shells. With the possible exception of the genus Paguristes, the direct application of force did not play a part in these shell fights. The signals exchanged by an interacting pair were very different in the two families. In the Paguridae, the attacker shakes the defending crab back and forth rapidly by a movement of its ambulatory legs, while the Diogenid aggressor strikes the defender's shell with his own by means of abdominal muscles. Measurements of shell-fighting pairs of Clibinarius tricolor indicated that smaller individuals very rarely win over larger crabs. Females have a slight advantage in shell fights, and that recently molted crabs are both more likely to be attacked and more likely to lose when attacked. 8. The sexual behavior of most species was observed and described. The precopulatory acts of the male are similar within the families. Diogenid males mainly rotate the female around an axis through the plane of her shell aperture, while pagurids jerk the female toward the male by movements of one of their chelipeds, which grasps a female ambulatory leg. The normal larval release-molt-copulate sequence was observed in most species, although pairs of Pagurus bonarensis consistently copulated while the female still had a complement of well-developed eggs. 9. A preliminary investigation indicated the presence of social order in groups of Clibinarius tricolor, Calcinus tibicen, and Pagurus miamensis, but the basis for this order was uninvestigated. Finis. That is the end of social behavior of the Paguridae and Diogenidae of Curacao by Brian A. Hazlett.